Hey everybody, welcome back. We are going to do some more 6.2. Today we're kind of getting into a little bit more, high level continuous random variables where we've been kind of working with whole numbers, recently with, amount of time that it took to assemble parts. Those were all kind of whole numbers. Could they be decimals? Absolutely. But today we're going to kind of dive into, okay, now we're working with some decimals. So example 7 talks about consider a random number generator that selects any number between 0 and 3. Decimals are allowed. So first it asks us to make a density curve and well, it doesn't ask us to make a density curve, but it does say in part A, the density curve is going to have a constant height throughout. And what is that height? So sometimes when you see density curve, it's a little confusing what it means, but let's just show you what we're looking at. So what I would do is I would draw kind of a number line and think about all your options, right? So it says that you are looking for any number between 0 and 3. So I know I've got 0, right? 1, 2, and 3. And I'm going to include all decimals in between that. So that's going to be really hard to do. Like, we're not going to actually write out every single decimal that lies in that interval. But what we are going to do is we're going to draw a density curve. And in this density curve, this is saying, like, basically we're trying to figure out what is the probability of selecting a number that falls within a certain range. So all of these, right, we are looking at a random number generator. And regardless of how you feel about random number generators, they all have the same probability of being chosen. So what we're going to do is instead of drawing, a bell-shaped curve, we're going to draw more of a constant curve. It's not even really a curve. It is more of a rectangle because all of these have an even, probability of being selected. So this is more of a uniform distribution versus like a roughly symmetric distribution. Okay. Now, the way I see it, the best way that I can explain what the height of this curve is we know that the overall area of the curve, the area underneath, right, this piece right here, the inside of the rectangle, is definitely going to equal 1 because that is our probabilities, right? So the area itself is for sure going to be 1. Every single probability, right, adds up to 100 or 1 if we're using decimals. And in this case, we kind of are using decimals. So if we know that the area is 1, right? And let's see this as like an actual rectangle. So this, the length right here, this definitely has a length of 3 because we go from 0 to 3. So that's its space. So if I know that my area needs to be 1, I know the length is 3. We have to think about, okay, what is the height? And since we know that like with a rectangle, area equals base times height, we know the area has to be 1. We know the base is 3, right? Or the width is 3. So that height definitely has to be 1/3 in order to make that true, right? Area equals 3 times 1/3. That's where I get that 1, and that checks out. So kind of an interesting, concept, but not bad when you look at it. So the height is going to be 1/3. Now these don't have to be units, but it does make the most sense in what we're looking at. Okay, so I am glad that we drew, somewhat of a little, diagram of our density curve because that's going to help us find these probabilities in B, C, D, E, and F. Okay, so probability that your value that you generate from the random number generator is less than 0.15. Now, if you have to put the diagram below, again, that's totally fine. If you want to go ahead and label, right, 0, 1, 2, and 3, you can, but I know that kind of takes time. What I would do though is I would remind yourself that your height is 1/3, so I would put a little 1/3 off to the side right there. Now this is helpful because we're trying to see, okay, what are we trying to find? So we're trying to find a number less than 0.15. So 0.15 is probably somewhere over here, right? 0.15, and I want a number less than that. So this is really the area that I'm kind of concerned with on this density curve. Now from here, all we're doing, honestly, is we're just doing a little bit of area work like we did over here where we said area equals base times height. So the base is going to be the distance from 0 to 1.5, right? So I know my probability of getting a value less than 0.15 is going to be 0.15 times that height of 1/3. Okay. And if you need, you could totally put it in your calculator like that. If you want to change the 1/3 to 0.33, you can do that too. But once you do that in your calculator, you get 0.05. So that is going to be my probability of getting a number that is smaller than 0.15. Now, let's go ahead and take a look at part C, because part C is very similar. So on part C, you're looking at the same exact diagram, right? If you need to draw in your numbers, again, you can. And remind yourself that your height is 1/3. But this time you're finding the probability that your number is less than or equal to 0.15. So we technically have not changed where we are on this curve, right? We are still at 0.15. But the way these density curves work is you can't really tell where 0.15 starts and where 0.15 stops. So I have no idea when I'm looking at the curve if I'm at 0.1499999 or if I'm at 0.150001. You have no idea. So actually these two probabilities from, this one and this one, they're actually going to be the same. So this probability still works for less than or equal to 0.15. So when you're looking at continuous random variables, that continuous part, you don't know where the exact values are. So that's why we can still say that the probability here is going to be 0.05 still. Now part D gets a little trickier. So same kind of concept, like you're still going to be doing base times height for all these. So we're still going to draw the picture in this one, but it's going to be a little bit different. So if I go to draw my picture right here, right, I'm at 0, 1, 2, and 3. There we go. Perfect. And same situation as all the other ones, right? My height is still 1/3. If I zoom in, the pens are too big. It's okay though. But I'm looking at the area between 0.2, which is somewhere over here. We're not really sure where, but it's definitely somewhere over here. And then 2.5, which is definitely somewhere over here. So this is the area I'm now looking at, which is it's a lot bigger now, right? Okay. So you kind of have to think about this a little bit. So if you start at 0.2, way over here, and you end at 2.5, you have to think about how long is this, this little side of the rectangle that I just made. So to get from 0.2 to 2.5, right, that space is 2.3 units away. Because instead of doing the whole 2.5, right, you're looking at 0.2 less than that, since you're not including from 0.2 to 0. Okay, so there's my base. I have my height, so I can go ahead and find this probability. So the probability that I get a value that is less than 0.2, greater than 0.2, but less than 2.5 is going to be that 2.3 times 1/3. When you multiply those two together, you get 0.77. So that's going to be my probability on that one. Okay, and that makes sense. Like we've expanded the area. It looks a little bit bigger, so that definitely makes a lot more sense here. All right, we got a couple more of these, so we're gonna do the same thing on E. So with E, same thing. I'm gonna go ahead and draw my diagram to help me. So 0, right, 1, 2, 3. If at any point you want to skip ahead because you're like, I got this, then go for it. You can skip ahead to example 8 because that's the other example that we're going to do in this video. Okay, still have a height of 1/3. This time I'm finding the probability that I get a number that is greater than or equal to 1.7. 1.7 somewhere over here, and I want all this area right here. Awesome. So just like the last one, I don't know what that side is, but I can definitely find it. So if I'm at 1.7 and I'm going to go all the way to 3, I know, right, this side is 1.7, so this side must be 1.3. because 1.7 plus 1.3, that's where I get that area, or the 3. Okay. So to find my probability, we should do an area again. So y is greater than or equal to 1.7, or sorry, yeah, greater than or equal to 1.7. I'm going to take the 1.3, I'm going to multiply it by my height of 1/3, and I get 0.433 there. Awesome. Now my last one's a little tricky. Okay. So I want to find the probability that I get exactly 2 on this crazy continuous curve. Now, remember way back in part B where I said, part B and C, where I said, you can't really see on the curve where, 1.5 starts and stops and where it is exactly that amount. That still applies in part F right here, where we're looking at find the probability, right, where y is equal to 2. We can't tell where that is. There is no way that we can do that. So that probability is actually 0 because it's impossible to see where it is exactly 2 when you're looking at these continuous random variables. Awesome. So now we're going to move on to something a little different. So on example 8, because this is, that was probably not that bad, just doing area of little rectangles. Not everything is in a uniform distribution though, right? Like we mostly work with things that are like roughly symmetric or follow the normal model, which if you were reading ahead, there we go, look at that. So we're going to kind of look a little bit more at more of a normal distribution, which is something that we're a little used to seeing. We're going to work on some skills that we worked on in the last video as well. So a company manufactures ships and small stereo systems. The time it takes required to pack the stereos is described by a normal model with a mean of 9 minutes and standard deviation of 1.5 minutes. The times to box can also be modeled as normal with a mean of 6 minutes and standard deviation of 1 minute. So we want to know what is the mean and standard deviation for the amount of time it takes to box and pack a stereo system. Okay. That's kind of like what we did yesterday. So a little review here. So you know what, if you want to go ahead and pause your video and do that on your own, that's fine, and check your work. Otherwise, you can also just skip ahead. I'm going to run through it pretty fast though, because we did it yesterday. So we are doing mean of box and pack, right? So box takes 6 minutes, packing takes 9 minutes. So 6 plus 9, hey, equals 15. So my new mean is 15 to box and pack a stereo system. Okay. Standard deviations. Remember from yesterday, we cannot add standard deviations. So sorry, but we can add their variances. So this time, you're combining 2, right? So mean of box and pack. There's not really a shortcut here. You're going to find their variances. So 1.5, that's standard deviation. Variance is squared. Plus 1. Standard deviation is 1, variance is just squared. And remember, when we do the standard deviation, we got to square root everything at the end. Perfect. So 1.5 squared plus 1 squared, and then square rooted again at the end. Again, I'm just kind of trying to save some time here. You can totally do that in your calculator. And when you do that in your calculator, you get 1.8. So 2 pack and box, right? A stereo. Wow, stereo. There we go. The mean is 15 minutes and standard deviation is 1.8 minutes. Perfect. Okay. Now for the new stuff, right? That was a little bit of review. New stuff. What is the probability that the amount of time that it takes to pack and box a stereo system is more than 18 minutes? Okay, a little different here. So we know that this distribution is going to be normal, right? We want more than 18 minutes. And so that's really hard to kind of like take all of your outcomes and find probability of 18, probability of 19, probability of 20. Something else that's kind of wrong with that is, could something take 18 minutes and 15 seconds? Absolutely. Could something take 18 minutes and 30 seconds? Could something take 19 minutes and 24.2 seconds? see where I'm getting. It's really hard to pinpoint like those very specific outcomes. So we're going to use that cue that we got earlier where it says this distribution is normal, and we are going to figure out what this probability is. So a couple ways we could do this. I'm going to do our first way. So one way you could do this, right? You could find z-score, use your normal CDF to find your z-score. That's totally fine. You could just do normal CDF. So I feel like we need to refresh. I mean, what I'm going to do normal CDF just with our calculator, just because like I feel like that's quicker. We kind of need to get in the hang of that, especially going into some of these harder units. So this distribution is normal. Let's go ahead and draw a normal curve. Okay. Our mean is 15. Our standard deviation is 1.8. So I'm going to go up by 1.8 everywhere and hope that I'm right, because it's kind of hard to do maths sometimes. There we go. I think I got it. Anyways, so yes, I know there's values below. I know this is not the best curve. It's fine. I'll take the time to draw a better curve like when I'm doing the AP test, right? So we are looking for 18 minutes or more, which is somewhere over here, right? Or more is going to be over here. I'm going to shade it with rainbow pen. We deserve some rainbow pen. Okay. So to find the area of that curve, right, I'm going to use my calculator. So I'm going to let myself know that I'm using, my calculator, and I'm using normal CDF, which we are used to. We've used it. It's just been a while, but we're going to be using normal CDF. Okay. Now you have all the pieces in your curve, right? Your lower is going to be 18. Your upper is going to be something we are never, ever going to hit. That's going to be 1,000. Okay. Mean is 15. Standard deviation is 1.8. Yes, you need all those labels or you won't get your points on your AP test. All right. So if you need a refresher on calculator, right? We are here. Pretty much all the distribution stuff lives in that second vars, because in the blue letters you see distr, right? So second, push the vars button. Normal CDF is your number 2, so we're going to go to number 2. We're going to enter all those things that we just said. So we're going to enter 18 in our lower. We're going to enter 1,000 in our upper. Our mean is going to be 15. Our standard deviation is going to be 1.8. And we're going to rock and roll. Boom. Okay, so my probability right here is going to be 0.048. Let's just roll with that number since that's a nice, easy round number. Sweet. Perfect. And then, you might want to make a nice sentence. I'm just kind of keeping an eye on the time, and I'm going, you know what? We've been here a while. So yes, right? We need to do the probability, right? It takes more than 18 minutes. To box and pack. Okay. And you're going to finish that sentence just so I can kind of keep this video nice and short. Awesome. Now, C says, what is the probability that packing 2 consecutive system takes over 20 minutes? You have to be really careful on these problems because of the wording. So this only talks about packing. So we're not going to use the same mean and standard deviation that we just used in part B because we're only looking at packing. Now we are also packing 2 consecutive systems. That means we're packing one right after the other. So we actually have to find that mean ourselves. So mean of packing 2. Well, if I go back to the beginning of my problem, it looks like the mean time to pack is going to be 9 minutes. So I'm going to do 9 2 times, right? 9 plus 9, or 9 2 times, whatever you want. Either way, you get 18 minutes for your mean here on packing. Okay. Now, I also have to do standard deviation of packing 2. Remember, you can't add standard deviations, but you can add their variances. So I'm going to do 1.5 make it a variance, I'm going to square it, plus 1.5, make it a variance, I'm going to square it, and square root that whole thing when I'm all done. Okay. Now, when I do that, when I square 1.5, square 1.5, and then add them together and square root, I should get 2.12. Awesome. Now I can go ahead and do the exact same thing that I did on that last problem. I'm going to draw my curve, right? Because number one, helpful. Number two, College Board loves to see it, please. So 18 going up by 2.12. So 20.12, 22.24. My curve's kind of ugly. I can't really go up more than 2 standard deviations, but we're just going to roll with it, right? Okay, now I need over 20 minutes. So 20 minutes is right here, right outside 1 standard deviation. It's right outside 1 standard deviation, so no, you can't use your empirical rule. You can't, just don't do it. But we're going to go ahead and find whatever this area is right here. We can kind of use that to estimate it though. But same thing as last one, right? We are going to be using our calculator. We are going to plug everything into normal CDF, okay? And we're going to label it everything. So lower is going to be 20. Upper is 1,000. Mean, 18. Standard deviation, 2.12. Okay. And since, in the last problem, I showed you how to put that in your calculator, I'm not going to, but I am going to just give you the answer. If you want to pause the video, plug it in your calculator, check your work, it's all good. Go ahead and do that right now. Otherwise, the answer that you should get is 0.173. Again, we're going to write a nice little sentence right there, but I'm not going to just for time because I'm kind of keeping an eye on it and we are getting kind of close to that 30-minute mark. So I'm going to go ahead and wrap up part D with us. All right. Now D says, what % of stereo systems take longer to pack than to box? Okay, so this is kind of a tricky one. So we want longer to pack than to box. Okay, so what we're looking at is what exactly is the difference between packing and boxing. So we haven't done a difference one yet, which is kind of exciting, but we're going to find the mean of packing minus the mean of boxing, because you're looking at those two differences and then you're seeing, okay, where exactly am I taking longer here? And we'll kind of talk about what that exactly looks like once we draw our curve. So mean to pack, right? When you're finding the mean of a difference, you are just going to subtract. So 9 minus mean to box is 6. So difference in those two means is going to be 3. On average, right, there is a difference of 3 minutes amongst these guys. On average, it looks like it takes about 3 minutes longer to pack than box, though. Okay, same thing with standard deviations, except you don't subtract standard deviations. You still add those variances. So 1.5, make it a variance. 1, make it a variance. And square root everybody. Okay. Again, just for time's sake, I'm going to go ahead and give you that answer, but make sure you square first, then add, then square root. Okay. And you get 1.8 there. So moment evolve I'm waiting for, right? What exactly does this look like? What exactly, are we trying to find in our calculator? So my mean is 3. Now this time when I set up my curve, I'm going to actually go, a couple standard deviations above and below. So 4.8 would be 1 standard deviation above. Another standard deviation above is going to be 6.6. Good thing there's only 2 6s. And then one more 8.4. I'm also going to go below. So to go below, right, 3 minus 1.8 is 1.2. And then I have 1.2 minus 1.8 is negative 0.6. Yes, I'm going to keep that in there because that is really important. Because remember, that represents like 0.6 less. And then I'm also going to do 2.4. I had to think for a sec. Cool. So I want longer to pack than box. Okay. Now I wrote a pack first, right? Here was pack, here was box. So if it takes longer to pack than to box, remember that this whole curve represents like the difference in time. So I need to start at 0. And the reason why I need to start from 0 is every single positive value on this curve is going to represent longer to pack than box. Every negative value on this curve is going to represent shorter, right, to pack than box. Remember how I said a few videos ago that order matters? This is where order matters. So you have to think about, okay, which one am I talking about first versus which one am I talking about second? So I'm trying to find this whole thing right here. This is the goal. Look at that rainbow. Sweet. So I'm going to go ahead and set this up with you. I'm not going to open up the calculator. I'm just going to assume that you're going to do it yourself. But if you need to go ahead and practice it a little bit, you totally can. If you're somebody who's using your table, that's totally fine. I just really want to master our calculator for this next few chapters of stuff because it gets kind of crazy. So we are using normal CDF. Okay. Our lower is 0 because that means it would take the same amount of time. And once again, we don't know where 0 starts and 0 stops. Our upper is 1,000. Our mean is 3 and our standard deviation is 1.8. Okay. We plug all that in, the magic happens, and we get 0.952. So what this means is about 95% of the stereo system are going to take longer to pack than box. And that's where we are going to end today. 95.2% of the stereo systems take longer to pack than box. Perfect. All right, that's all I got for today. Next video we're going to dive into some crazy probabilities. So thanks for watching. Enjoy the rest of your day.